All right, so this video here is just sort of a brief introduction on how our temperature scales came to be. So during the course of this unit, we will discuss or study three different scales. One is the Fahrenheit scale, which is the one that we're familiar with here in America, as that's how we use, or what we use to measure our temperatures for the most part. The Celsius scale, which is used predominantly in most of the other parts of the world, would be a scale created by Anders Celsius, and we're somewhat familiar with that, I would think, from our science classes. And then there's the Kelvin scale, which actually is the SI unit of measure for temperature, is actually Kelvin. So we'll talk all about that as this unit progresses. All right, so I guess it all starts with Daniel Fahrenheit, who was a scientist who back in around 1724 came up with a scale with the sole purpose really of being able to share his findings on the studies of heat and heat transfer with other people. At the time, there was no set standard for temperature. And so if he discovered something in his lab and he wanted to check to make sure that it was right, something we call peer review nowadays, he would publish or provide his information to others, and they could go ahead and redo his experiment, see if they came up with the same results. But the problem was, how do you measure temperature if no one has a set scale? So that's what he set out to do. So the Fahrenheit scale worked. And by the way, a couple decades later, Anders Celsius will kind of do the same thing. His scale would be different. It would follow a different mathematical model, one that was kind of easier to understand. And the Kelvin scale, William Thomson will adapt Celsius's work for the most part with a couple of different approaches and end up with the Kelvin scale. All right, well, let's just talk about Fahrenheit for now. So in order to do this, Fahrenheit went ahead and he made a thermometer in this fashion. He took a glass container, glass tube, if you will, right? And he went ahead and he filled that tube with some mercury, which is a liquid metal, which will happen to, by the way, if it gets warm, it'll increase in volume. We call that thermal expansion. And if it gets cold, it'll contract. And so he went ahead and he filled the mercury up to a certain level. And then he capped the top. All right, so now he evacuated all the air. So this is sort of a vacuum in the center. And now if you went ahead and you put that thermometer, let's say he put it into boiling water, what would happen is the energy would go into the mercury and it would cause that mercury to rise to a certain point and then stop. And what he figured out was there's got to be a couple different benchmark temperatures that I need in order to set the scale. And he used for his benchmarks two items that were commonly available to him. One is boiling water. So he could boil the water at any time, and he ended up getting a value. So he put a notch in his blank or non-labeled thermometer that every time he put the mercury reservoir into the boiling water, the mercury would thermally expand up until this particular point. All right, and he did it over and over again so that it was pretty much consistent. And then he would go ahead and take the same thermometer and he would place that thermometer into the colder water. And of course, when that happened, what we found was the mercury shrank as the heat left the mercury and went into the colder water. In this case, it wasn't just cold water, it was ice water. And if you stirred the ice cubes around in the ice water, you would always get a set temperature, he assumed. And when he would go ahead and put the mercury thermometer into that ice water, he would also get the same temperature every time he did that. And he would put a notch as well. So in the end, he had two notches. He also used, by the way, two other benchmarks. One was under his arm, so he used body temperature. And then he used the coldest temperature he could create in a lab, which was a mixture of salt and water and ice. And so we'll talk more about that later on. But the fact is he was able to get four different temperatures and worked out mathematically a consistent pattern of added energy to added temperature change. And today we know that the boiling water, or the boiling point of water in the Fahrenheit scale, is 212 degrees Fahrenheit. And on the Celsius scale, and on the freezing point of water is 32 degrees. So just to recap, the ideas of thermal expansion play a role in this, in that as energy goes into the mercury in the thermometer, today they don't use mercury. We won't in our class. If we have a bulb thermometer, that is just alcohol that's been colored red, like rubbing alcohol, it's been colored red. Um, but it does the same thing. If it gets warmer, it expands through thermal expansion, and it does so at a set rate based on what the material is. If it cools, it contracts, and that's basically how the thermometer works. All right. We know that whenever whenever you put objects with different temperatures together, heat will always flow from the warmer object to the cooler object until they have the same temperature, or what we refer to as thermal equilibrium. This is the second law of thermodynamics. So when we go ahead and we take our mercury thermometer and we place it into the cold water, heat would leave the thermometer and go into the cooler water until we had the same temperature, and that's going to cause the mercury level to drop. If we put it into boiling water, same concept will go ahead. The heat will go from the warmer object, the boiling water, into the mercury thermometer, causing the mercury to thermally expand or rise up until the temperatures were the same, or where we're at thermal equilibrium. All right, so now what we know is that the freezing point of water in the Fahrenheit scale is 32 degrees Fahrenheit, right? 32 degrees Fahrenheit. And the boiling point of water is 212 degrees Fahrenheit. Anders Celsius kind of did the same thing. He used a different mathematical model and a different scale, so his freezing point of water was 0 and his boiling point was 100. Celsius pattern, or Celsius's model, was much to the liking of William Thomson, but he started thinking about this. Think about 0. Now, we have this idea called the kinetic theory of matter, which means that all matter is made of tiny particles that are moving. And as we have read, the motion of the particles is really a function of the temperature of the particles. So if they're moving fast, you have a high temperature. If they're moving slow, you have a slow temperature. So if you think about that, 0 on a temperature scale should really mean 0 motion of the particles. And that means you can't get any colder, right? You can't get any more non-moving than not moving. But when Thomson looked at the Celsius scale, 0 was just the freezing point of water. When water freezes, it can get colder than its freezing point, much colder than its freezing point. And so we have negative values for degrees Celsius, right? So whenever it is below 32 degrees Fahrenheit, the Celsius reading is negative, whatever, -2, -5, whatever it might be. And for Thomson, that didn't make any sense. He said 0 in a true temperature scale should represent no motion whatsoever. And so on his scale, he came up with this idea or concept of absolute 0. That is, that you remove so much energy from any substance that the particles inside no longer move at all. And so that we call the absolute 0. And only on the Kelvin scale is that value 0. But he liked the mathematical model of Celsius. So it turns out that in his new scale, to get the Kelvin value, all you need to do is take the Celsius value and add 273. All right, that's how it ended up working out when he made his scale. And there's a lot of time and effort and experimentation and mathematics that went into this. But basically, that means that the boiling point of water in Celsius is 100 plus 273, or 373 Kelvin. They don't say degrees Kelvin, they just say Kelvin. And then the freezing point, it would be 0 plus 273, or 273 Kelvin. Conversely, if I want to go from Kelvin to Celsius, then I'm going to take my Kelvin value and I'm going to subtract 273, right? Just this opposite. So 0 minus 273 is negative 273. So the temperature at which all particle motion stops on the Celsius scale is around negative 273. It's actually negative 273.15. It is a theoretical point. We don't actually get that cold, but we can get pretty close, like within fractions of a degree close to it. And then on the Fahrenheit scale, there's an equal value. This is something that you can calculate, right? You know how to use the formulas now, so you can calculate that. But on the Celsius scale, it's around negative 459, negative 459 degrees Fahrenheit. That is the absolute zero on the Fahrenheit scale. So all of these scales work. All of these scales have value to them. And when we look at the physics of the behavior of gases, or the ideal gas law, then in order for those set of formulas to work for us, we need to make sure that we have our values in the Kelvin scale. In fact, it was working with gases and the science behind thermodynamics that William Thomson was able to come up with the scale. So if you have any questions on this, we can discuss that next time I see you.